This is session C5, Particle in a Box, Part 2. Last session, C4, Quantum Mechanics for Spatial Problems, was general. Now we will use that material and get specific for particle in a box in one dimension. For the energy eigenstates of particle in a box in one dimension, we will show that the energy eigenfunctions are orthogonal and that our choice of energy eigenfunctions are normalized. We will find the probability density and the probability current. We will find various expectation values and uncertainties. In this lecture, we will solely deal with energy eigenstates. In lecture C5, we will treat superposition states. In order to do the things that we need to do in this lecture, we will need to evaluate various integrals. But you don't need to know calculus to follow this material, or even to do the integrals yourself, as I will show you. We will be doing different definite integrals of the form integral with respect to dx, the position variable, from x equals minus infinity to plus infinity of wave function capital psi conjugate times some function of x and t. Now, for a particle in a box in one dimension, psi and psi star are 0 everywhere except for x within the box in the interval 0 to a. So we don't need to integrate from minus infinity to infinity because the integrand will be 0 over everywhere except within the box. So we can restrict the evaluation of the definite integral to 0 to a. Furthermore, for all but one of our integrals, the time dependence will cancel, and we can use the time-independent wave function, lowercase psi of x. No time dependence. And for this lecture, for particle in a box in one dimension, lowercase psi of x, we've chosen it to always be real. So the complex conjugate of lowercase psi is the same as lowercase psi. Also, for these particles in a box in one dimension, energy eigenfunctions, we will always be able to pull a factor of 2 over a out of the integral. So we will be evaluating definite integrals of the form 2 over a, integral from 0 to a, of lowercase psi of x, we don't need the complex conjugate because it's real, times some function of x with respect to x. So we'll need to evaluate 2 over a integral from 0 to a, some function f of x dx, and we need to get its indefinite integral, or its antiderivative, capital F of x. And then when we have that, we need to do the substitution from 0 to a to get 2 over a, capital F of a minus capital F of 0. That will be our mathematical task to help us understand the physics, the quantum mechanics, of particle in a box in one dimension. Given some specific lowercase f of x, we need to find capital F of x, its indefinite integral or antiderivative. There are multiple ways to do this, even without knowing calculus. This is a possible time to take a break. Probably for you, the best way to do that is to use the website wolframalpha.com. It has a free online calculator and it can do derivatives and integrals. We can do indefinite integrals such as integrate sine squared of k of x, or definite integrals, such as integrate sine squared k of x from 0 to a. Let's see that. This is the website wolframalpha.com. In this input box, we give it the command integrate sine squared of kx. It's smart enough to know that we mean to integrate that with respect to x, not k, and it gives us the indefinite integral. Integral of sine squared of kx dx is x over 2 minus sine of 2kx over 4k, and then in light gray it says plus constant. We will always be taking a definite integral, so from 0 to a, in which case this constant will always be eliminated, so we won't have to worry about that. Now, if you want to take this result and copy it into a Word document or whatever, you can click on plain text, and you can copy this plain text to clipboard, or if you scroll down a little, you get the output in a special Wolfram language format, and you can copy that to a clipboard. Now, if you wanted, we're always going to be doing a definite integral, but for the most part, we're going to use wolframalpha.com to produce the indefinite integral, and then we'll substitute for 0 and a. But if you prefer, you can have wolframalpha.com do that work for you. Integrate sine squared kx from 0 to a, and it gives you the result of doing that. And if you want to do that, that's perfectly fine. So our task is for different things that we want to understand, to find the correct function lowercase of f, and then integrate it to produce capital F of x. We can integrate it using wolframalpha.com or other techniques. You may know calculus, you may know how to integrate it, and then evaluate it from 0 to a. Now, other ways of integrating without wolframalpha.com. If you do a lot of this and other physics and other mathematical problems, you can install and use some computer algebra system application on your computer, whether it's a Windows or a Mac. You have fewer choices if you're a Linux user. Now, Mathematica, Maple, and MATLAB, you have to pay for those. But GNU Octave is freeware and mostly compatible, mostly a copy of MATLAB. If you're going to do a lot of physics on your computer, and you want to relieve yourself of a lot of the math, you might look at Maple or Mathematica, which both cost. You may be able to get a student license for, I think, on the order of $100. Now, another perfectly fine approach to doing integration is, when you're experienced with calculus, is to guess the correct integral and then verify it by taking its derivative. When you have a lot of experience, this actually works pretty well, because you end up knowing things like, you know that the derivative of x squared is 2x, and the derivative of sine of x is cosine of x. And with some experience, you can often guess the correct integral and verify it. we can integrate manually with some help if you're even if you're not experienced with calculus. You can do this by using some rules, and then verify it by taking its derivative if you know how to do that in calculus. There are tables of integrals. There are books of integrals and tables online, and Wikipedia has multiple pages of lists of integrals, one of which is lists of integrals of trigonometric functions, which we will need because we know that for particle in a box in one dimension, the wave function is always going to have a sign of kx in it. It is often needed or helpful to be able to do trigonometric substitutions to make your integration easier. For example, sine squared x is always identical to 1 minus cosine of 2x over 2 for any value of x. It's a trigonometric identity, and I should have used an identity. Instead of equals, it's identity. And Wikipedia has a nice, very thorough list of trigonometric identities on this page. For some of the integrals we're going to do, it is helpful to know integration by parts. That if u and v are functions, say of some other variable like x, then the integral of u dv is equal to u times v minus v du. And you can turn that into a definite integral as well. But when you do that, you have to evaluate the product uv from 0 to a. Now, you don't need to do any of these things. You can just trust my results. But if you want to verify my results, do it any way you please. And if you don't know calculus, the wolframalpha.com website should work just fine for you and not require you to know calculus. In this lecture, I'm going to use different techniques in different places so that if you want to learn, it teaches you something about integration techniques and dealing with wave functions. But if you're not interested in that, you can just go to the answer that I give and use that, and that's just fine. This is a possible time to take a break. So from now on, for the rest of the lecture, we're going to use the normalized time-independent and time-dependent energy eigenfunctions for particle in a box in one dimension, which we gave in a previous lecture, probably C3. So both functions are 0 when x is less than 0. They're 0 when x is greater than a. They're a sine function inside the box, inside the well, from 0 to a. They both have a specific prefactor, square root of 2 over a, which I've said previously is the correct normalization, and in this lecture we're going to verify that that's the case. Now, lowercase psi is not dependent on time, it's time independent, but uppercase psi is dependent on time. It's an energy eigenfunction, so the time dependence is a complex exponential, e to the minus I e sub n t time over h bar, as we know before. We've seen that before for dealing with energy eigenfunctions. And as we know before, k sub n is n pi over a, with quantum number n ranging from 1 to up to plus infinity, and the energy E sub n of the energy eigenvalue E sub n is h bar squared k sub n squared over 2 times the mass. So it's pi squared h bar squared over 2ma squared times quantum number n squared. Now, I've said that that's normalized, and in the previous lecture, C4, I gave you the formula for telling whether something is normalized. So let's use that now to verify that it is normalized. And we could do that with lowercase psi sub n, but if we do it for uppercase psi sub n, we will learn a little more and it will be applicable to lowercase psi sub n as well. So let's verify that uppercase psi sub n is normalized by calculating its inner product as we defined it in last lecture, C4. So this is inner product notation, inner product of psi sub n with itself. And that is, we defined that previously, so this is not just equal, it's defined as the integral over all space dx from minus infinity to plus infinity of the complex conjugate of psi sub n times psi sub n. Now, for contributions for x less than 0 or x greater than a, those contributions are 0. So we only need to do the integral from 0 to a. So let's rewrite that. In this case, particle in a box in one dimension, the inner product is equal, it's not defined as, but it is equal in this case to the integral from 0 to a. Now we could just substitute for psi sub n because we know what that is. Psi sub n is square root of 2 over a sine k sub n x e to the minus I e sub n t over h bar. We have to substitute it here, and we have to substitute it inside parentheses and then complex conjugate it. But that's not difficult to do. Square root of 2 over a is real, so we don't need to do anything to get its complex conjugate. Sine of k sub nx is real, so we don't change it for its complex conjugate. But for the complex exponential, we have to negate the exponent. So we get e to the plus I e sub n t over h bar. Remember that e sub n, t, and h bar are real. So now this is the integral that we need to integrate. We can reorder this. Square root of 2 over a times square root of 2 over a, that's 2 over a, and it's not dependent on x, so we could pull it out of the integral. This sign and this sign, we can bring them together, sine squared k sub n of x. Here's this complex exponential, here's this complex exponential. Now these two complex exponentials cancel one another out. E to the plus I e t over h bar, e to the minus I e t over h bar, they cancel. Multiplying them together, we get 1. So the time dependence has canceled because we were taking the inner product of an energy eigenfunction. So now our task is to integrate sine squared k sub n x dx. And we can do it in any of the techniques we talked about before. So one of the techniques was to use trigonometric identities. Sine squared knx is identical to 1 minus cosine 2k sub nx over 2. That's a trigonometric identity. And then we need to integrate this. Or we could just integrate sine squared k sub n of x. Wolframalpha.com is perfectly happy to do that. If we ask for the indefinite integral, we will get x over 2 minus sine of 2k sub nx over 4k sub n, and then we would have to evaluate that from 0 to a. Let's look at wolframalpha.com and see that that's the case. So this is the integral that we saw before. We did the indefinite integral, and we came out with this indefinite integral, and that agrees with what we've put here. Now, we need to evaluate that from 0 to a. Now, first we plug in a for x. So that we keep the 2 over a. This x becomes a over 2, minus sine 2k sub n. This x becomes a, divided by 4k sub n. And then we need to subtract the substituting 0 in this expression. But when we substitute 0 in, x over 2 becomes 0. 2knx becomes 0, and sine of 0 is 0. So in this case, substituting the 0, that part goes away because it is 0, and this is our correct answer. Now, let's look at if we had gone to Wolfram alpha and had it do the definite integral. Integrate sine squared kx from 0 to a. We get this. It did correctly substitute a for x, and it knew how to evaluate the 0 part, and so we're all good. Now, k sub n is special, and we didn't tell wolframalpha.com anything about k, but k sub n times a is equal to n pi. We have a constraint. Earlier we said that k is n pi over a, k sub n. So if we substitute for k sub n pi over a, then this a and that a would cancel. We would get 2 times n times pi, which is an integral multiple always of 2 pi, and the sine of that is always going to be 0. So sine of that is always 0. So this term, 0 over 4k sub n, is always going to be 0. We're going to get 2 over a times a over 2, and that's 1. And so we ended up with the inner product of capital psi with capital psi is always 1. That's what we intended to prove. When it's always 1, when the inner product is always 1, we say that is normalized. So capital psi sub n of x and t is correctly normalized. And we could do exactly the same procedure for lowercase psi sub n of x, and it also would be correctly normalized. Now, this didn't happen just magic. In lecture C3, we had an arbitrary multiplicative factor b with the sine term, and at some point in that lecture I said, okay, let's substitute that as square root of 2 over a. And I said that would achieve normalization, and now we see that yes, square root of 2 over a is the correct prefactor to achieve this normalization. So good work. However, normalization is unique only up to an arbitrary phase factor. If instead of substituting, instead of using a prefactor of square root of 2 over a, I had used minus square root of 2 over a, that also would be normalized. I also could have used square root of 2 over a times e to the minus I alpha for any real alpha, and that wave function would also have been normalized. So you have some free discretion in how you normalize things. Generally, when there's no problem, you will find it easiest to choose a real value and a positive real value, but you don't have to do that. All things will work out fine with any of these normalizations. So if you have a bound state wave function and you need to get the normalization, Start with an arbitrary multiplicative factor, calculate the inner product, including that factor. That result is not necessarily going to be 1, it's going to be some function of the multiplicative factor. In general, it's going to be, some number times b squared, magnitude of b squared. And then when you set that to be 1, you will have a constraint on that multiplicative factor. But you will have a constraint on its magnitude. You will then still be free to set its phase if you wish. Now that was for bound states. If you try to calculate the inner product for an unbound state wave function like a free particle, the integral over all space will diverge. It will be infinite. Unbound state wave functions are non-normalizable. We still use them, we still need them, but we have to be careful when we use them. We have to be careful what we mean about things like probability density. And don't think you can just put the free particle into a very large box to get rid of the infinity. It would get rid of the infinity, but we've seen that particle in a box has quantized energy levels, unlike the free particles. So don't rush to do that naively and think that you haven't changed the problem. You have changed it subtly. This is a possible time to take a break. Now that we've proven that all of the energy eigenfunctions that we're going to use are all normalized, let's calculate the probability density. And we said in the previous lecture that the probability density is particularly easy formula when we know that the wave function is normalized, and now we do. We know that our energy eigenfunctions are normalized, So the probability density, rho sub n, of x and possibly of time is equal to the magnitude squared of either capital psi sub n of x and t or of lowercase psi sub n of x, because it's not going to be dependent on time. If you take the magnitude squared of psi sub n, you're going to find out that the time dependence cancels. And so for these energy eigenfunctions, the probability density of x is 0 when x is less than 0, it's 0 when x is greater than a when we're out of the box. And in the box, it is 2 over a sine squared k sub n of x. So it is different for different n's within the box. The probability density for these energy eigenfunctions is independent of time, as they should be. The energy eigenstates are stationary states. Note that here I was careful to say x less than, so I didn't actually give a value for x equals 0 or a value for x equals a, but that value would be 0. If inside the box, if we let x tend towards 0, this probability density is going to tend towards 0. And if we let x tend toward a, we would get k sub n a, and that's going to tend toward n pi, and that is going to tend toward, sine squared of that is going to tend toward 0. So if we take the limits, the probability density at 0 and at a is going to be 0. The probability density is continuous at the hard wall boundaries. Let's graph the probability density for n equals 1, 2, and 3. Here's inside the box 0 to a, x going in that direction. The green curve is the ground state. Probability density outside the box is 0. and then we get a sine squared with a peak in the middle of the box, no nodes, goes down to 0 at the other side of the box. That's for n equals 1 ground state. I'm not putting any numbers on here. You can go back to the formula if you want numbers. Now for n equals 2, the wave function has a node at the middle of the box, and the probability density has a node in the middle of the box as well. So the blue curve goes 0, and the probability density goes up and then down to 0, and then up and down to 0. For n equals 3, there's 2 nodes. So 0 up, 0 up, 0 up, and 0. Note that each one of these probability densities is symmetric around the center of the box. This one is symmetric. This one is symmetric. This one is symmetric. When n is odd, there is no node at the center of the box. When n is even, there is a node at the center of the box. For n greater than 1, there always are some nodes. So there are some positions, x, where the probability density is 0 inside the box, except for the ground state. The particle can never be here at the middle of the box if we're in the n equals 2 state. It can be very close, it can be arbitrarily close, it can be infinitesimally close to the center, but it can never be identically at the center because there's a node there. This is a possible time to take a break. Now the probability current, we have a formula for calculating it, and it involves the imaginary part of, capital psi sub n star times the derivative of capital psi sub n with respect to x. And we could do all that, but in the last lecture, I said that when the time-independent portion of the wave function is lowercase psi sub n of x, when it is real valued, the imaginary part of the expression is going to be 0, and the probability current will be 0. So the probability current is 0 for energy eigenfunctions of particle in a box in one dimension. The probability current conservation equation is true with both terms being 0. This is a possible time to take a break. Particle in a box in one dimension energy eigenvalues E sub n are non-degenerate. If we have an energy eigenvalue E sub n, there is one and only one state for that energy, eigenstate for that energy. So it is non-degenerate. And we said in the last lecture that energy eigenfunctions psi sub n of x and psi sub m of x will be orthogonal when they correspond to different energy eigenvalues. So what we want to show here is that the energy eigenfunctions psi sub n and psi sub m are orthogonal for n not equal m. We're going to show that by actually doing the integral. So let's show that using the inner product. Inner product of lowercase psi sub n with lowercase psi sub m we're using the time-independent wave functions, it's going to be true that the time-dependent energy eigenfunctions, capital Psi, are also orthogonal. And if you're not sure, if that's not obvious to you how that's going to happen, then go through that case to prove it to yourself. Don't leave yourself be uncomfortable with why that's true. So we want to take the inner product, the integral over all space minus infinity to plus infinity of the complex conjugate of lowercase psi sub n with lowercase psi sub m. But they're both 0 outside the box, so we can restrict the integral to 0 to a. We can substitute what psi is, and here we have psi sub n, so I've substituted k sub n as n pi over a. We still need to take its complex conjugate. Here is psi sub m. K sub m is m pi over a. Now the complex conjugate of square root of 2 over a is unchanged. Sign is unchanged. There's nothing imaginary or complex here, so it is real, and its complex conjugate is equal to itself. We could take the square root of 2 over a's and pull them out into 1, 2 over a. So now we need to integrate from 0 to a sine n pi x over a sine m pi x over a dx. And you can do this in Wolfram alpha. Maybe let's go there and see what we get. So we get a result. If we wanted to do that from 0 to a, we could. In this lecture, I'm going to actually go through and use a trigonometric substitution. This sine times this sine, there is a handy trigonometric substitution for it. 1/2 times cosine of this result with n minus m minus cosine of this result with n plus m. I know that the integral of cosine is sine because the derivative of sine is cosine. We have to include a prefactor, the correct prefactor, because it wasn't cosine of x, it was cosine of n minus m pi x over a. So we have a prefactor here. And if you want to go through it, this is the correct integral, or you can verify it with Wolfram alpha. Now, in doing this integral, I relied on n not being equal to m. Now, we were only looking to find that the wave functions were orthogonal when n was not equal to m. But in doing the integration, I actually needed to rely on that, because otherwise, if n were equal to m, this would be sine of 0, but there would be a 0 in the denominator, so that would be undefined. So we are only looking at the orthogonality condition for n being different than m. Now, for particle in a box, n and m are both positive integers. Neither of them is negative, so n plus m will never be 0. So that is okay. Now we need to do the substitution 0 to a. But when we do the 0, this is going to become sine of 0, and this is going to become sine of 0, so that part's going to go away. We substitute a in for x, and that'll cancel with the a in the denominator in both sine terms. So we get this expression. Sine of n minus m pi, sine of n plus m pi. But n and m are both positive integers. So n minus m is an integer, It could be 0, but it's definitely an integer. It could be a positive integer, it could be 0, it could be a negative integer, but it doesn't matter. It is an integer times pi, and the sign of that is always 0. Likewise, sine of n plus m pi is always 0, so we do get that the inner product of psi sub n and psi sub m equals 0 when n is not equal to m. Energy eigenfunctions psi sub n and psi sub m are orthogonal for n not equal m, as they should be, since their energy eigenvalues E sub n and E sub m are different because all of the energy eigenvalues for particle in a box in one dimension are non-degenerate. And we did say in the previous lecture, C4, that when we have energy eigenfunctions with different energy eigenvalues, they will be orthogonal. And we've proven here that they are for particle in a box in one dimension. Now, we've previously shown that the energy eigenfunctions are normalized, and now we've shown that they're orthogonal. So those are the two conditions we required to say that they are orthonormal. Orthonormal meaning they're orthogonal when n is not equal to m, and they're normalized, and each individually normalized. So they are orthonormal. This is a possible time to take a break. Now, so far we've always dealt with position representations of wave functions, psi of x. It is possible to produce momentum domain representations, phi of p and time. It's possible to do that using a Fourier transform. This is the correct Fourier transform. It can be simplified here using the convention that p equals h bar k. If we were to do that work and end up with a momentum domain representation, we could also determine the probability density in momentum representation. Probability density rho sub n of momentum p and time t. In a real course in quantum mechanics, you would use Fourier transform. You would be able to do the momentum domain representations. That's important to some problems. However, these are more complicated than we want to undertake, and there's nothing essential to us in those results. So it would be possible to do, it would be very messy, and not give us much value, so we're not going to do it. But I want you to be aware of, if you were taking a physicist course in quantum mechanics, you would also deal with momentum domain representations. This is a possible time to take a break. Let's calculate the expectation value of energy. When we do the expectation value of energy, the operator that we're using is the Hamiltonian h. So operator h hat. And we're taking the expectation of it. This is the integral that we defined in the last lecture. We are going to be doing a bunch of expectation values, so we're going to actually be doing the integrals. It may be obvious, it will be obvious to some of you, if you look at that integral, that the expectation value of the Hamiltonian for energy eigenfunction psi sub n is going to produce the energy E sub n. If it's not obvious to you, then please go do that integral, that calculation. It's the easiest possible case for me to say go do it. All the other ones are more complicated, so I will be doing them for you. But in this case, I think you can actually do it and will learn something by doing it. But if you don't want to do it, just take my word for it that the expectation value of energy. Remember, anytime we do expectation value, we have to say with respect to what wave function. And here we're doing it with respect to the energy eigenfunction psi sub n. The expectation value of energy for energy eigenfunction psi sub n is the energy eigenvalue E sub n. And I'm going to put in eigenvalue. The expectation value of the square of the Hamiltonian operator, h squared, or h operating on h, that would be the energy E sub n squared, as you can also easily prove. So the expectation value of the square of energy is E sub n squared. In the last lecture, I also defined the uncertainty for any observable operator. So the uncertainty in energy is this formula. The uncertainty in energy is the square root of the expectation value of h squared, but I just said that that is E sub n squared, minus the square of the expectation value of h. Well, the expectation value of h is a real number, E sub n, which we can square. The expectation value of any observable will be a real number, so we can say squared, we don't have to say magnitude squared. So we get E sub n squared minus E sub n squared, it's 0. It's the uncertainty in energy for these energy eigenstates is 0. The energy eigenstates have definite energy, 0 uncertainty in energy. An energy eigenstate is a state of definite single energy. If you measure the energy of a state that is an energy eigenstate, you will get that definite energy as your measured result, and the state will remain unaltered by your measurement. So you can remeasure it again if you want. In general, you can't expect remeasuring to give you the same result, but if you remeasure energy on an energy eigenstate, it will, assuming an ideal measurement capability. The uncertainty in energy E is 0 because the states we examined are energy eigenstates, eigenfunctions of the observable Hermitian operator H. In our next lecture, we will deal with superposition states for particle in a box, and the uncertainty in energy will not be 0. This is a possible time to take a break. Let's calculate the expectation value of position x for the energy eigenfunction psi sub n. Where do we expect the position to be, on average, in a particular state? Now, you might know the answer to this without doing the integral, and that's fine. But we're going to do the integral and then check it against our belief. So we need to, expectation value of operator x is the integral from minus infinity to plus infinity dx of the complex conjugate of the state, psi sub n star, and then the operator goes in the middle. In this case, the operator is x, and then the state, psi sub n, of x and t. Now for particle in the box, we only need to integrate between 0 and a because it'll be 0 everywhere outside there. And the time dependence, when we do this complex, we're dealing with an energy eigenstate only in this lecture. And so when we do the complex conjugate, the time dependence is going to cancel between this complex conjugate term and this term. And the operator in the middle, x, has nothing to do with time, so we'll be able to move the time across and it will cancel. So we can deal with the time independent wave functions. Now we can substitute the time independent wave functions psi sub n. We substitute here, we substitute here. This is real, so the complex conjugate is itself. It's already the real part. So now we need to integrate this with x in the middle. But this x is not doing anything fancy operating on the wave function to the right. So we can actually commute the order of this, rearrange them. We can pull the 2 over a out. We can move the x to the left, still inside the integrand. X, so we need to integrate x sine squared k sub n of x. And let's use Wolfram alpha to do that. We could have it do the definite integral, but let's integrate x sine squared kx. We get this result. We can copy that into our Word document. If you check it, you should find that I've correctly transcribed it here. It looks complicated, but the result is not going to be complicated. We need to evaluate that from 0 to a. So first we plug in a. We take x, plug it in a, x, plug it in, get a, x, plug it in, get a, x, plug it in, get a. Now we need to substitute the zeros. 0, 0, 0, 0. Now let's see how we can simplify our life. We 2k sub n a is going to be 2n pi. The sign of that is going to be 0. I'm going to leave the k sub n's for the moment, except inside a sine or a cosine. 2k sub n a is going to be 2n pi. The cosine of that is going to be 1, so here we get 1. Here we have 0 times 0 minus 0, and then we have cosine of 0. Well, cosine of 0 is 1, so we have to keep that. Now, here we have a minus in front, so we have minus 1 over 8 k sub n squared plus 1 over 8 k sub n squared. So that part goes away. The 0 part goes away. So we end up with minus, minus, so that's plus 2 over 8. We keep that. K sub n times k sub n over k sub n squared, that goes away. A times a squared. 2 times 2 is 4 over 8 is 2 in the denominator. A squared over a is a. So we end up with the expectation value of x equals a over 2, which is independent of n. So for every energy eigenfunction of particle in a box in one dimension, the expectation value of x is a over 2. Now we did the integral to show that that's true. the expectation value of position is the middle of the box, the middle of the well, for all values of n. Now, we could have guessed, it should not be surprising, and we could have guessed that the potential energy function is symmetric around the midpoint. And so the expectation value had to be equal to the midpoint. It couldn't be on either side of the midpoint because the potential energy function was symmetric. However, note that when n is even, like n equals 2, the energy eigenfunction has a node at x equals a over 2. So the expectation value of position is the midpoint of the box, but there's a node in the probability density at the middle of the box, because the probability density is the expectation value occurs in the middle because the probability density is symmetric around the midpoint. So in these cases, even n, a measurement of position will never give exactly the value a over 2 because it's a node. But it could be arbitrarily close to a over 2. It could be anywhere in the well. It can't be 0, it can't be a. In this case, it can't be a over 2, but it could be arbitrarily close to 0. It could be arbitrarily close to a over 2, and arbitrarily close to a. But it can't ever be exactly a over 2 for even n. This is a possible time to take a break. Let's calculate the expectation value of momentum for energy eigenfunction psi sub n. So now our operator is going to be p. The integral is going to be the same from minus infinity to plus infinity. We're going to integrate with respect to dx. We have a wave function psi sub n. We have to take its complex conjugate here on the left. The operator is p hat. And we've indicated before that for momentum in the x direction, the operator p hat is h bar over I times the partial derivative with respect to x. So now in the middle we have an operator here which we can't move around. It operates on the psi sub n on the right. We can't change the order of things here. Now, it's still going to be true that we only need to integrate from 0 to a because the wave functions are 0 outside the box, so we can change that. We could put in the time dependence, but we're dealing with an energy eigenfunction, so the time dependence is a complex exponential of time. The derivative with respect to x doesn't do anything for time, so we could move the time dependence across, and it will cancel with the time dependence of the complex conjugate. So our life is simpler. We can use the time-dependent wave function, psi sub n, which is real in this case, so its complex conjugate is itself. We still have to do the momentum operator operating on psi sub n. So let's substitute in psi sub n here and here. Now, we could do this. We could do the derivative of sine, and we will get a cosine. And then we could rearrange, and we could have Wolfram alpha do that integral, and that would be just fine. Here I'm going to use a trick that those of you who know calculus, I want you to recognize this trick. If you don't use calculus, don't worry about it. Just move ahead to the result. We can move 2 over a to the left of the integral. We can move h bar over I to the left of the integral. And then we end up with partial derivative with respect to x of sine of n pi x over a dx. Now there's no more time, so I could change this to ordinary derivative with respect to x. So I'm doing a derivative with respect to x of this and then dx. And if you know calculus, that's the same thing as if we were doing a differential of sine n pi x over a. So now we have sine n pi x over a d sine n pi x over a. Well, we can imagine that's u du, and the integral of that is u squared over 2. So the integral of this is going to be 1/2 sine squared n pi x over a. And we need to evaluate that from 0 to a. And you would get the same result if you actually took this derivative and then plugged it into Wolfram alpha and do the result. You would get this result. Now we need to evaluate it between 0 and a. When we plug in a, we're going to get a over a. That part's going to cancel. We're going to get n pi. But the sine of n pi is always 0, and sine squared of that is always going to be 0. And when we substitute 0 in for x, we're going to get sine squared of 0. That's going to be 0. So the part within the square brackets here is always going to be 0, so the expectation value of momentum is always going to be 0 for these energy eigenfunctions. So as I said, we could also have taken the partial derivative and then done the integral. That would have worked out fine. Now we could have made a reasonable guess that the expectation value of momentum would be 0 based on either of two facts. The energy eigenstate is a bound stationary state. How can the expectation value of momentum be in one dimension, bound stationary state in one dimension? How can the momentum be anything, the expectation value of momentum be anything but 0? Or 2, notice that the momentum operator introduces a factor of 1 over I. There's still a factor of I in the denominator here. But there's nothing else. I mean, this integral is real. This evaluation is real. If it was anything but 0, then the expected value of momentum would be a pure imaginary number. But I'm telling you that the momentum operator is a valid Hermitian operator, which you have to take my word for it. So it's a valid observable. And I said before that the expectation values of observables are always real numbers. So the only way to turn this 1 over I into a real number is if we multiply it by 0. So we could have guessed that the expectation value of momentum for a particle in a box in one dimension, energy eigenfunctions, is 0. This does not mean that a measurement of momentum would produce a 0 value. It means that positive and negative values of momentum have equal probability. If you were to try to measure momentum on this system, you could get 0, you could get any, I think pretty much any positive value of momentum and any negative value of momentum. So what does that expectation value of momentum mean? It means if you had very many identical ensembles in the identical energy eigenstate psi sub n, and for each one you measured momentum and you tallied them all, and then you averaged them all together. Some would be 0, some would be positive, some would be negative. You average them all together. You have very many systems that you each took one measurement on. The average value would tend to 0 as the number of systems, the number of systems in the ensemble got to be very large, like infinite. This is a possible time to take a break. We want to calculate the uncertainties in position and momentum. And I gave you a formula for those uncertainties, and to do that we first need expectation values of the squares of the operator, expectation value of x squared and expectation value of p squared. First, let's calculate the expectation value of position squared for the energy eigenfunction. Expectation value of x squared, it's the operator in the middle, x squared. We know that we can change this to 0 of a. We know that the time dependence goes away. We know that we can reorder this to be x squared sine squared. Now we just need to do it. It's a little messy. So in this case, let's have Wolfram alpha not only do the integral, but we'll have it do it from 0 to a. Save us some steps. So integrate x squared sine squared kx from 0 to a. It knows how to do it, no problem. We can copy that result in, and then we can work with it. So it's already taken care of the substitution of 0 and a. The only thing we didn't ask it to do is know something special about k. We'll do that ourselves. So I'm going to keep k sub n except inside sines and cosines where I'm going to evaluate it. So k sub n times a is n pi, 2n pi. Sine of 2n pi is always 0, that's 0. Sine of this is always 0, that's 0. Cosine of that is always 1, that's 1. So now we have this expression. Let's get rid of those zeros, make it look simpler. So this is the same as that, just with the zeros gone. We can simplify this. We can, 4 and 6 have a common factor of 2 times 2 is 4. We could take that out of the denominator, so we get a 2 here, a 3 here, a 6 in the denominator. We could take this a away from both terms in the numerator, so we get 2a squared k sub n cubed minus 3k sub n over 6k sub n cubed. Let's pull a squared out to the left, and on this left term we get k sub n cubed over k sub n cubed, so that goes away. 2 over 6, that's 1/3. Now I pulled a squared out of the left, but there wasn't one here, so I have to put it in the denominator here. We can get rid of 1 k sub n, so we end up with k sub n squared in the denominator. 3 over 6, that's 1/2 with a minus sign. So we end up with k sub n squared a squared, and so we end up with this. And now we could substitute. We know that k sub n a is n pi, so we could substitute that. So the expectation value of x squared is a squared times quantity 1/3 minus 1 over 2 n squared pi squared. Now, this expression has its smallest value when the negative term has its largest value, and that will be for n equals 1. For values larger than n equals 1, the denominator will increase, the total quantity will get smaller. We will be subtracting it, so the expression will get larger. So this expression increases as n increases, but it's bounded because as n goes to infinity, this term becomes 0, so it increases with n, but it's bounded. This is the value of the expectation value of x squared, and we will need this and use this later when we calculate the uncertainty in x. This is a possible time to take a break. Let's calculate the expectation value of momentum squared for the energy eigenfunction. Momentum squared, momentum squared. Now momentum is h bar over I, partial derivative with respect to x. We have to write it twice. We can change the integral from 0 to a because we know that the wave function is 0 outside the box. We'll keep the time dependence for the moment here. H bar times h bar is h bar squared. 1 over I times 1 over I is minus 1, so we get minus h bar squared, second partial derivative with respect to x squared. We could just do this. We could plug in capital psi. We could take the second derivative. The second derivative of sine is going to be minus sine. We could do that. We could use Wolfram alpha. No problem. That's a perfectly fine way to do it. But I want to show you a trick here. This integral is now inside the well. What is the Hamiltonian inside the well? It is minus h bar squared over 2m, second derivative with respect to x squared. There's no potential. The potential energy is 0 inside the well. So this expression is the same as 2 times the mass times the Hamiltonian. Okay, well, why did we bother to do that? Because now the Hamiltonian operating on an energy eigenfunction, we know what that is. It's the energy eigenvalue times the eigenfunction. H psi equals E psi. So now the operator part is done. And 2me is a constant value, has nothing to do with x. We can pull it outside to the right. It's also real, and in this case positive. So we pull that out, and then we end up with an integral from 0 to a of psi conjugate psi. But we already know that psi sub n is normalized. So this integral is going to be 1. So the uncertainty in momentum squared is 2m e sub n. We know what e sub n is. We could substitute it. And then the 2 times the mass is going to cancel. And we end up with uncertainty in momentum squared is pi squared h bar squared over a squared times n squared. This increases without bound with increasing n. This is a possible time to take a break. Now let's calculate the uncertainty in position x for the energy eigenstates. The definition of uncertainty is the expectation value of the operator squared minus the square of the expectation value of the operator. We've already calculated these. We only need to substitute in. So here is the expectation value of x squared, and then minus the expectation value of x is a over 2, middle of the box. We need to square that. We can pull, we have a factor of a squared in common. We could pull that out as a. Here we end up with 1/3 minus 1/4. That is 1/12. So we end up with this expression. the uncertainty in position x. It has its minimum value for n equals 1. It increases with n, but it is bounded. The particle is bounded to within the box, so obviously the uncertainty in position has to be bounded too. It's in the box. We know it's in the box. So let's look at the minimum and maximum values. For n equals 1, we get this value on the right, and the uncertainty in x is always greater than or equal to that. It's only equal to it for n equals 1. When n equals infinity, we get this value on the left, and the uncertainty is always less than that. Let's plug in some. Let's actually calculate these. 1 over square root of 12 is 0.289. If we do this calculation, we get 0.1807. So the uncertainty in x is always between these two values, between 0.18a and 0.29a inside the box. This is a possible time to take a break. The uncertainty in momentum, we can calculate that. We need the expectation value of p squared. Well, we calculated that. We need to square the expectation value of momentum, but the expectation value of momentum was 0. So we get that the uncertainty in momentum is pi h bar over a times n, which increases without bound with increasing n. So for very large n, we have large uncertainty in momentum. Now, of course, our solution is only valid non-relativistically. So if you plug in a really huge value for n and you get a really huge uncertainty in momentum, you could get a momentum value which is relativistic, but you've exceeded the non-relativistic limit of our using the Schrödinger equation. Let's calculate the uncertainty product, uncertainty in x times uncertainty in p. We have those two values, we just need to multiply them together. Here's the uncertainty in x, here's the uncertainty in p. When we multiply them together, the a in the numerator and the a in the denominator cancel. This h bar moves to the left. We can move n and pi into the integral as n squared and pi squared, so we get h bar square root of pi squared n squared over 12 minus 1/2. The n squared and pi squared canceled there. The uncertainty product increases without bound with increasing n. Its minimum value will be when n equals 1, and that will be h bar square root of pi squared over 12 minus 1/2. You can calculate that, and you will get 0.5679 h bar. And that is greater than 1/2 h bar, greater than h bar over 2. Heisenberg uncertainty principle told us this is a system, it is a state. Momentum here is in the x direction. The uncertainty in x times the uncertainty in p sub x has to be greater than or equal to h bar over 2 by Heisenberg's uncertainty principle, which we said always applies in Schrödinger's equation. So all energy eigenfunctions for particle in a box in one dimension do satisfy the Heisenberg uncertainty principle, as we said it better. Now here we're doing particle in a box, but if we were to do simple harmonic oscillator, which is more complicated for sure, and classes do it and books do it, that system, that potential is very special. The ground state of the simple harmonic oscillator is special in that the uncertainty in x times the uncertainty in momentum is equal, actually not just greater than, but equal to h bar over 2 for that ground state, for that potential energy function. But that is very special and, if not unique, in actually equaling h bar over 2. Now, let's recap a little. Every expectation value that we calculated produced a real value because we were always using observables, Hermitian operators, even though I still haven't and never will define Hermitian operator for you. For that, go to a MIT 804 or a book. All expectation values that we encountered were independent of time because we only used states that were energy eigenstates. They were stationary states. This is the end of our treatment of particle in a box in one dimension energy eigenfunctions. Next lecture, C6, we will look at a superposition state for particle in a box so we can learn something about superposition states without doing too much work, too much math. This is the end of session C5.